polynomial that doesn't have a coefficient in front of it. So 6x squared minus 17x plus 12. You maybe would guess and check on that. It's not going to be easy, but take a minute and see if you can guess and check and find that within, I don't know, a minute. Raise your hand as soon as you get it, just so I can get a feel of. So I know I got Aiden and Andrew. Anybody else? Okay. One of, so 3 of you. So this one might be a situation where guessing and checking isn't really all that efficient, and I can see why, because number 1, you're not sure if it's 1 and 6 or 2 and 3, and then you're not sure if it's 1 and 12 or 2 and 6 or 3 and 4, or any opposite order of those, since your first 1 and 6 and 2 and 3 are not the same. So that's a lot of tested combinations. So let's go to your alternative method if you kind of start to get frustrated with guessing and checking because there's just way too many options to sift through. What do you guys do next? Did you do like splitting middle term sound familiar to you? No? All right, let me explain, and then we'll see if your teachers just called it something else. So I call it splitting the middle term because we're going to look for a way to split up negative 17 so that grouping will work. So I look for 2 numbers that are going to multiply to get this product. And this particular product is 72. So I'm looking for things that would multiply to get positive 72 that would combine to get negative 17. I'm going to worry about the signs later. For starters, I'm just going to look at my combos to get me to 72. Is it 24? 4 and 18. 6 and 12. 8 and 9. So obviously they need to multiply to get positive 72, but they need to combine to be a negative. So whatever pair we choose here, it's going to have to be a double negative. What pair there, if it's a double negative, will combine to give you negative 17? Bailey?
8 and 9. Right,
so, but it's going to obviously be a negative 8, negative 9. So we would split the middle term and make this 6x squared minus 8x minus 9x plus 12. As you know, factoring is the opposite of simplifying. So the fact that we just sort of uncombined like terms, we did it in a way such that grouping would work. So if we group the first 2, what's the GCF we should be taking out, Mackenzie? Of the first 2 terms? What's the GCF of the first 2 terms? 2. 2's in 2x, correct. So if you take out a 2x, you're left with 3x minus 4. And on the second grouping, we would take out what, Trista? Negative 3. Very good. If that leads with a negative, we always take out a negative. And that's going to leave us with 3x minus 4. And because those 2 sets of parentheses match, if we look at this particular line as a binomial, here would be my first term, here would be my second term. Okay, they have a GCF of 3x minus 4. So I would pull that 3x minus 4 out in front. And when I strip this first term of a 3x minus 4, I'm left with just a 2x. And when I strip the second term of a 3x minus 4, I'm left with a minus 3. So after all of that, it was a 3 times 2 to get you the 6. Now, does that look familiar, ring any bells? Did you do that? Okay, what did you call it? You don't know what that was called? No one? What do you think, Julia?
I don't remember.
No? No, nobody? I don't know. I'll have to ask Mrs. Ziggy what she called that. I don't do the box method. I know that you guys probably explored that option, and you're welcome to use that if you want. I don't know, something about getting to upper level maths and dropping, like starting to draw little boxes just makes me nervous. I just feel like we should be coming away from that. But if you're visual oriented and you like those boxes, that's more than fine. So I call that splitting the middle term, because you have to find the proper way of splitting up negative 17. And you could split up negative 17 in an infinite number of ways. But like if I did split it up into negative 10 and negative 7, that wouldn't work. So you have to have it get the product of 6 times 12, and it has to have a sum of negative 17. Okie doke, so here's our answer. Any questions? All right, 2 is going to be a straightforward grouping, so we're going to take out an x squared, leaves us with x minus 1. On the second grouping, I'm taking out a negative 5. Again, that second grouping led with a negative, so I'm going to take out a negative, and that leaves me with x minus 1. And so those 2 sets of parentheses match, so the binomial, if you see it that way, has a GCF of x minus 1 that can be taken out in front, and that leaves us with an x squared minus 5. In number 3, it often can happen to us where we overlook this because we get so into seeing special patterns and using our strategies, but you always want to look for a GCF first, because if you don't notice the GCF, you're going to be at a loss for what to do with this. But once you take out your GCF of a 2, now a special pattern should come to light and be a little bit more clear to you. 81x to the 4th minus 1 is the difference of perfect squares. So we would further factor the difference of perfect squares into conjugates. And what would those look like, Sarah? Very good. And then always when you look at your final factors, you want to make sure that those final factors are fully factored themselves. And one of these is obviously still factorable. Which one is that, Olivia? Right, so that's going to factor, keep going, Olivia, into what? Correct. And we still have the 9x squared plus 1. So that one, after the GCF and the 2 layers of difference of perfect squares, ends up having 4 factors in the end. 4 is a special pattern, and you could guess and check with this. You could split the middle term, but if you notice that the first term is a perfect square in a trinomial, what's the square root of that? 8x. And the last term is a perfect square. What's the square root of that? 1. And if you take the product of those 2 perfect square roots, 8x and 1, the product of 8x times 1 is 8x, and the middle term is double that, that's that perfect square trinomial pattern that we kind of spent some time the other day looking at from the other direction. So if you notice 8x and 1, and then the middle term is double that product, then you've got that pattern for a perfect square trinomial. And what makes something a perfect square is that you can take the square root of it. So this would become, and whatever that square root is, 8x, and this has a square root of 1, but because it's a minus sign in the middle, it's going to be minus 1. That factors back into that binomial squared. Okay, and that's what makes that a perfect square trinomial. It's a trinomial that can be written as something times itself. The definition of a perfect square. Okay, the sum and difference of perfect cubes. I know that you had to memorize those last year. So recognizing perfect cubes and then understanding how this breaks up. The rule is a binomial and then a trinomial. Who can tell me what this would factor into, remembers this from last year? Did you do this? Did you factor difference of perfect cubes and sums of perfect cubes? You think you did. Oh boy. What's your first name? Marissa. Go ahead. I'm going to go down here because you're giving me this one, right? So this is the general rule. Say what you said again. Yep. Now, can you share with everybody else how you remember it, strongly enough, obviously, that you remember this from last June? Okay, so that gave you the signs. So that gave you, if it's plus, that gave you same, opposite, always positive. So, that's what she said. Okay, how did you remember each individual term? Do you remember that? So, same, opposite. That helps you remember the signs. But the cubed root of the first term gives you that. The cubed root of the second term gives you that. And then once I'm done with that, I just use this. I square this a for the first term, I square this b for the last term, and I multiply the two together for the middle term. I don't double this time, right? Not to confuse this methodology with this one. I don't double this time. I just multiply these two together, and that gives me the middle term, and that's the opposite sign one. So in this particular one up here, what is the cubed root of 8x cubed, Nate? (2x) and 125. Keep going. 5. And what sign? Plus. Same. And then here's where, and this is the way I remember it, I square this one to give me the first term there. Julia, what's 2x when you square it?
4x.
Very good. And then I square this 5 for the last term. That one's a little bit easier, 25. And then my middle sign is the opposite, and I just multiply 2x times 5. I get 10x, and that's my middle term. I'm tempted to say that this portion will never be factorable further. Like, I don't think I've ever seen it. I'm tempted to say that because I haven't yet proved why that would be, but I don't think I've ever seen it where this is factorable further. This is tempting though, because you see maybe this would be one of these situations, because that is a perfect square with the square root of 2x. That is a perfect square with a square root of 5, but this middle term is never double that product. It's always exactly that product. So I don't think it will ever be further factorable. But if we come across one, make sure we point it out because I'm curious. Number 6, when we look at this, I think we probably all see initially, just because we're so trained to do this, 4 terms. We think group the first 2, group the second 2. But that's not actually going to work here. So, and I know you played around with this a little bit last year, of grouping things a little bit differently than you're used to. So in this particular one, you'd want to maybe pick up on this special trinomial right here, which is factorable, because this is a perfect square trinomial. This has a square root of x, this has a square root of 5, 5x doubled gives us 10x. So this factors into x minus 5 squared minus 36y squared. And then what you should see here is the difference of perfect squares, right? Which factors into conjugates. So the square root of this is x minus 5, and then we've got a square root of 6y. So we do plus 6y, and then an x minus 5 minus 6y. And so seeing those as conjugates. Any questions? All right, really basic rules. Difference of perfect squares factors into conjugates. Difference of perfect cubes rule mimics the sum. Just we got to switch our signs. Same, opposite, always positive. And then a perfect square trinomial, we just have to see this middle term as being double the product of the square roots, is going to be a plus or minus b squared. So if this middle term is a plus, then that's going to be a plus. If this middle term is a minus, then that's going to be a minus. So I just threw some steps there at the bottom in kind of what you should always handle first, factoring out a GCF. I guess in this case, when I was saying that this will never be factorable further, if, God forbid, you forgot to take out a GCF in the beginning, this may eventually have a GCF. Not sure about that. Again, we're supposed to take the GCF out right away so we don't forget it at the end. But then 2 terms, you're looking for special patterns, any one of our 3 special patterns, the sum or difference of perfect cubes, and we don't have a sum of perfect squares, only a difference of perfect squares. 3 terms, we're looking to FOIL, or again for special patterns. And we could add to that splitting the middle term if that's necessary on a harder example. And then if it's 4 terms, we're looking to group or for special patterns. Okay, so the factoring in pre-calc, we're not going to sit here and ask you the basic examples that you from time to time were asked last year in Algebra 2. So you built a little bit in Algebra 2. Now we kind of leave those really easy examples alone. We just assume that you've got them, and we work a little bit more heavily on tougher cases. Okay? John, we have the same birthday.
I know.
You knew that?
Well, yeah, you went on the board. So
Oh, I didn't look at your guys' pedals yet. I looked at I want my teachers. I'm going to wait till I know you a little bit better to go back and look at all that. But just so you know, May 9th, in case you're wondering. All right, this is definitely new. I don't believe you've ever done this before. So factoring with rational exponents. So I guess I'll go back to an example like with whole number exponents. If you were asked to factor this, I know you'll all get this. What would you take out, Morgan? X squared. And what made you choose to take out x squared? Right, because it's the smallest exponent on the variable there. That's kind of what they all overlap by. That's the way I always thought of it. But if you think just quantity, you take out the variable with the smallest exponent that you see. So that rule is going to be no different when you're dealing with fractions. What here is which one of these exponents is the smallest? What's smaller, 3/2 or 1/2? 1/2. So that's going to be the GCF that I take out in front. And then I know you do this a little bit more naturally when you're looking at familiar numbers like whole numbers and familiar exponent terms that have whole number exponents, but what you're technically doing always when you take out a GCF is you're dividing a 2 out of 162x to the 4th. You're dividing a 2 out of -2. So to go back to really the basis of what you are doing when you take out a GCF, to figure out what's left, we actually want to divide a 1/2 out of this term. So you might want to write that down to visualize what's happening, because it's going to be more challenging with fractional exponents. What will x to the 3/2 become when you divide out x to the 1/2, and why? Joe? And why are you subtracting? Because you're following your exponent rules. You're dividing common bases. So when you divide common bases, you just subtract exponents. 3/2 minus 1/2 is 2/2, right? And we all know that 2/2 is just x to the first power. So we just have x. I'm not really showing all that work. So maybe you want to write yourself a note that subtract exponents 3 halves minus 1 half is 2 halves, which is just 1. And then obviously I'm not writing to the first power because you just don't need to. And then on the second term, this one's a little more straightforward because anything divided by itself is just 1. And there's your answer. That's definitely new, right? We've never done that before. Okay, so you see the one kind of added stipulation that we focus on in algebra or in pre-calc. And then it gets more challenging because now we have negative exponents. What's smaller, negative 1 half or negative 3 halves? Negative 3 halves. Okay, so that is what we are going to take out. Now also with this one, our base is not just x. Our base is x plus 5. So we are going to factor out, and I'll save some space and put it down here. We are factoring out x plus 5 to the negative 3 halves. Are we only going to 20 after? Oh, good. So I'm going to factor that out, and then I'm going to have to leave space for what is left of each term once I divide that out. So this is something I absolutely think you should kind of get in front of you concretely on paper. So I'm going to kind of think, when I have this term, and I'm going to divide out my GCF of x plus 5 to the negative 3 halves, again, I'm dividing common bases. So I have to keep that same base, but come up with what my new exponent is going to be. Negative 1 half minus negative 3 halves is negative 1 half plus 3 halves is 2 halves, again, which is just 1. So that x plus 5 is being raised to the first power, which I'm not going to write, minus, and again here on the second version, because that in and of itself is the GCF, anything divided by itself is just 1. That would technically end up being x plus 5 to the 0 power. Anything to the 0 power is 1. If you went through the exponent rules. Now, this one requires some follow-up as well. So the plot thickens. In here, we can simplify because we can combine like terms. And here, we're not allowed to have negative exponents in our final answer. So a couple things need to happen. This needs to move to a denominator to handle the negative exponent. So we have x plus 5 to the positive 3 halves. That moved to the denominator. And then in our numerator, x plus 5 minus 1, of course, is just x plus 4. And that's the proper format. Okay, so when you see those, take your time, maybe jump back to the video, fast forward, and kind of watch and listen to this explanation again, because that will take some time to sink in. And just like any math, the first time you learn something, and you first do a problem for practice, it's going to take you 4 or 5 minutes to kind of wrap your head around. And then the next time you do it, it'll take 2-3 minutes. And then that process, the more you do, becomes more automated and it becomes second nature. But you have to put that time in up front on new topics to make sure you're processing and letting that really sink in. Have you ever heard that about reading a new vocab word? That you supposedly need to read it 7 or 9, I don't remember the number of times before it becomes second nature and you know what it means? No? Well, the first time you read it, you actually look it up in the dictionary. If you're doing it properly, I should say. The second time, you're like, oh, I know I've seen that before, but I don't remember at all what it means. You look it up in the dictionary. The third time you see it, maybe you look it up, maybe you slightly remember, and then the more you see it, then it becomes just second nature. It's a good analogy, I think, for how we learn math. All right, that's my thought of the day. Next example. We just have a mixture of x's and y's here. Why do I have this one here? What are your thoughts when you look at this? Oh, I know. because at first glance, I was just thinking, I was in the GCF mindset. At first glance, this does not have a GCF, so I'm thinking, what the heck did I put it here for? But go back, it's just a trinomial. If you go to your steps, factor out the GCF, okay, there's not one. 2 terms, 3 terms, 4 terms, this is 3 terms. Look to FOIL, split the middle term, if you can guess and check. I think we can guess and check on this one, right? There's really only one way to make 2x squared happen. That's 2x times x. And there's really only one way to make 3y to the 4th happen. Although with 3, it could be 1 and 3 or 3 and 1, which is going to make a difference because these two are different. So what's going to give us 7? 1 and 3 or 3 and 1? So this will give us 7, right? 6 on the outer, 1 on the inner. And we want it to, well, technically, I guess y to the 4th could be y times y to the 3rd, or y squared times y squared. But because your middle term has a y squared, we want our outer and inner to also contain a y squared, so that's obviously going to be y squared. I don't know if I've ever seen an example where a variable being raised to an exponent hasn't been cut perfectly in half. Do you know what I mean by that? So, and oftentimes I don't usually see exponents being raised or variables being raised to an odd exponent. Maybe in the beginning, but once a GCF is pulled, they're usually all even. And then when you kind of split them, you just split them in half. Anyway, we have, they're supposed to multiply to positive 3, so we know it has to be either a double negative or a double positive, and we look at the middle term to realize that they need to combine to be negative 7, which can only happen with a double negative. So, you know, those trickier examples where they kind of give you a blend of variables, you've seen them before, but the next exercise definitely has a GCF, so we would take that out first, just a y, and we're left with y to the 6th plus 1, which is the sum of perfect squares, which you can't do anything with, but also those perfect squares also happen to be perfect cubes, yes? So keeping my GCF out in front and setting up the structure for the sum of perfect cubes, binomial times trinomial. What is the cubed root of y to the 6th? Mitch? The whole number 2? Let's see. The cubed root of y to the 6th. 3 goes into 6. Y squared. Very good. And the cubed root of 1 is obviously 1. So we have the same sign. And then when we jump to our trinomial, I square the first term. That's going to be y to the 4th. I multiply them together. I get y squared, but it's the opposite sign. And then always positive. The last term squared is just 1. And then that trinomial is not factorable. Are we good? And last but not least, we've got a trinomial. But if you obviously look at this, it's pretty clear that they all have a GCF of x plus 1, so it kind of puts you into the problem in the middle of the grouping process. X plus 1 gets pulled out in front, and then the first term, when you strip it of its x plus 1 or divide out that x plus 1, is just a 10x squared. Second term is just a minus 7x. Last term is just a minus 6. Now that trinomial, is that factorable? The quick test, if you, rather than just starting to guess and check because you're not sure if there's even an option, the quick check would be to do that same process. Can we find two numbers that multiply to get negative 60? That's your A times C. That combine to get negative 7? Multiply to get negative 60. obviously I have to mess with the signs a little bit, but now because it's going to be a negative 60, these signs need to be opposite. So do any of these have a difference of 7? Andrew? 5 and 12. And so since I've already kind of done this work and found the pair, I am not going to sit there and guess and check. I'm just going to split the middle term. So because it's a negative 7, which one has to be negative? The 5 or the 12? 12, very good, the bigger number. Minus 12x plus 5x minus 6. I'm going to group the first two terms, take out a 2x. I'm left with 5x minus 6. Take out, what do I take out here? Just a positive 1. If there's nothing to take out a 1 or a negative 1, depending on that leading sign. And then, of course, the 5x minus 6 is match. So that's one term. The other is 2x plus 1. And I just got really wrapped up in the splitting of the middle term process, which happens. Don't forget to bring your GCF that you initially took out down into your final answer, because that's kind of a silly spot to lose credit. Okay? So we up the ante on factoring just a bit. Okay? Your homework is there, and your quiz will be tomorrow. Are there any